What if you could step into a machine today and travel 100 years into the future, or even back to the dawn of time itself? Picture standing beside dinosaurs as they roam ancient forests, or witnessing the birth of stars in a cosmos still raw and young. Time travel isn't just the stuff of science fiction. It's a puzzle that has captivated scientists, philosophers, and dreamers for centuries. And here's the wild part. According to the laws of physics, it might not be entirely impossible. The universe is far stranger than we often realize, and the very fabric of time might hold secrets that could rewrite everything we think we know. Think about the stories that have shaped our imagination, tales of heroes slipping through time, of accidental journeys to eras long gone or not yet born. These aren't just fantasies, they're echoes of a deeper human longing to break free from the unrelenting march of seconds, minutes, and years. What drives this obsession? Maybe it's the desire to fix past mistakes, to glimpse the future, or simply to marvel at the vast, untouchable stretches of history. But what if the universe actually allows it? What if time isn't the rigid, one-way street we've always assumed? That's where things get thrilling. From Einstein's theory of relativity to the mind-bending possibilities of wormholes, science has uncovered tantalizing clues that time travel might not just be possible, it could be hiding in plain sight, woven into the very laws of reality. But with these ideas come paradoxes that twist logic itself. What happens if you go back in time and prevent your own birth? Could you alter history with a single step, or does the universe have a way of keeping time intact? These aren't just thought experiments, they're real questions that physicists grapple with today. And in this video, we're going to explore them all. The theories that could make time travel a reality, the paradoxes that threaten to unravel it, and the breathtaking implications of bending time to our will. Strap in, because we're about to take a journey through the most fascinating mysteries of the cosmos. Einstein shattered our simple view of time when he revealed that it's not a fixed, universal clock ticking the same for everyone. Instead, time bends. It stretches and compresses depending on how fast you're moving or how close you are to something incredibly massive like a black hole. This radical idea, called relativity, means your experience of time might be completely different from someone else's. Take astronauts on the International Space Station, for example. They're orbiting Earth at nearly 17,500 miles per hour, which sounds unthinkably fast to us, but in the grand scheme of the cosmos, it's just a gentle cruise. Yet, because of their speed, time actually passes slightly slower for them than it does for us on the ground. Over months in space, the difference adds up. It's tiny, just fractions of a second, but it's real. Their clocks literally fall behind ours, proving that time isn't as rigid as it feels. This phenomenon, known as time dilation, gets even wilder near extreme gravity. If you could stand on the edge of a black hole, where gravity warps space-time like a bowling ball sinking into a trampoline, time would crawl to a near standstill from your perspective. To someone watching from a safe distance, though, you'd appear frozen, barely moving at all. Meanwhile, for you, the rest of the universe would seem to speed up. Centuries could pass in what feels like minutes. It's not magic, it's the universe obeying its own rules, but here's where it gets truly mind-bending. If you could harness this effect, say, by traveling close to the speed of light or skirting a black hole's gravitational grip, you might leap forward in time without aging. A trip that feels like 5 years for you could land you 100 years in Earth's future. That's not science fiction, it's the inevitable consequence of how space-time works. Of course, we don't have the technology to pull it off yet, but the universe isn't stopping us. It's almost as if time travel to the future is written into the laws of physics. We just need to find the keys. The catch: going backward is another story. Relativity opens the door to forward time travel, but reversing the flow, returning to the past, throws up paradoxes that make physicists squirm. What if you went back and stopped your own birth? Would you vanish, or would the universe somehow correct itself? These aren't just fun thought experiments. They're serious obstacles that suggest time might have a one-way sign, at least for now. But before we dismiss the idea entirely, there's another astonishing possibility hiding in the equation's wormholes, cosmic shortcuts that could fold space-time like a piece of paper, connecting distant moments in time. And that's a journey for another segment. Wormholes sound like something ripped straight from a sci-fi epic, tunnels burrowing through the very fabric of space-time, connecting distant corners of the universe in an instant. But here's the astonishing part: they aren't just fantasy. According to Einstein's equations, these cosmic shortcuts could exist. Picture space-time as a stretched-out bedsheet. Normally, getting from one side to the other means traveling the long way across. But if you could fold the sheet so 2 points touch, you might punch a hole straight through, creating a bridge. That's a wormhole, a theoretical passage where distances collapse and time itself might twist into a loop. The math behind them is shockingly elegant. When Einstein and physicist Nathan Rosen explored the implications of general relativity, they stumbled upon structures now called Einstein-Rosen bridges, wormholes in their simplest form. These wouldn't just link two places in space, they could, in theory, connect different times. Need to visit ancient Rome or witness Earth 1,000,000 years from now. A stable wormhole might serve as your portal, but before you start packing your time travel suitcase, there's a catch. The universe seems to hate shortcuts. Natural wormholes, if they exist at all, would likely be microscopic, snapping shut faster than you could blink. Keeping one open would require something exotic like negative energy or matter that defies gravity's pull. And that's where physics gets dicey. Negative energy isn't just rare, it might be impossible outside quantum scales. Even if we could harness it, stabilizing a wormhole would demand astronomical amounts of it. Then there's the pesky issue of radiation. Quantum effects near the throat of a wormhole could unleash deadly bursts of energy, turning your time tunnel into a cosmic death trap. But let's say you somehow dodged all those hazards. Now you're staring down the mother of all paradoxes. If you stepped through and altered the past, would reality unravel? Or would the universe enforce some twisted version of consistency, bending events to ensure your actions always fit into history? For now, wormholes remain tantalizing ghosts in the equation's possible, but just out of reach. Yet the fact that they're even mathematically plausible hints at how little we truly understand about spacetime's secrets. Maybe one day we'll uncover the missing piece that turns theory into reality. Until then, they remind us that the universe is far stranger and more wonderful than our boldest stories. Black holes are the ultimate cosmic time machines, not because they let you hop across centuries, but because they warp time itself into something unrecognizable. Imagine getting close enough to peer over the edge of one, where gravity's pull becomes so fierce that not even light can escape. Here, the fabric of spacetime isn't just bent, it's stretched to its absolute limit. Time, which usually feels so steady and predictable, starts to drag like syrup. For someone brave or reckless enough to hover near the event horizon, seconds might crawl while the rest of the universe races forward. A single hour for you could mean decades or even millennia passing elsewhere. This isn't just theoretical. The science behind it is anchored in Einstein's general relativity, which predicts that extreme gravity doesn't just pull on objects, it warps time itself. The closer you get to a black hole, the more time slows down relative to the outside world. It's like standing still on a speeding train. From your perspective, everything around you seems to blur into overdrive. The movie Interstellar brought this idea to life with its depiction of Miller's planet, where 1 hour equals 7 years back on Earth. While the film took some creative liberties, the core concept is shockingly real. Time dilation near a black hole wouldn't just be dramatic, it'd be catastrophic for any human traveler. But here's the haunting twist: from the outside, your descent wouldn't look like slow motion. To a distant observer, you'd appear to freeze at the event horizon, your image stretching and reddening as light struggles to escape the black hole's grip. You'd fade from view, but not because you've stopped moving. From your perspective, you'd plummet inward, torn apart by tidal forces long before reaching the singularity. The universe has a cruel irony when it comes to black holes. They bend time in ways that tease the possibility of time travel, but the price is annihilation. Yet this extreme distortion hints at something profound. If we could survive the journey, maybe with futuristic tech or by riding a theoretical, gentle black hole, we might leap forward in time just by skirting its edges. No wormholes or paradoxes required. Of course, the universe doesn't make it easy. Black holes are less like time machines and more like cosmic shredders, reminding us that the laws of physics guard their mysteries fiercely. But in their terrifying depths, they offer a glimpse of how fluid time really is, and how much we still have left to discover. If you could step into the past and change one event, just one, what would it be? Here's where time travel gets messy, because even small alterations could unravel reality itself. Take the grandfather paradox. Imagine going back in time and accidentally preventing your own grandfather from meeting your grandmother. No grandparents, no parents know you, but if you never existed, who went back in time to disrupt their meeting? The contradiction snaps back on itself like a broken record, leaving physicists scratching their heads. It's not just a plot hole for time travel movies. It's a genuine problem that suggests the universe might have safeguards against such meddling. Then there's the bootstrap paradox, a loop so strange it feels like cosmic plagiarism. Picture finding a time machine in your garage, then traveling back to give it to your past self. Where did the machine originally come from? There's no answer. It's a closed loop with no beginning or end. Like a song that writes itself or a book that appears out of thin air, the bootstrap paradox erases causality, the very glue that holds reality together. Scientists call these self-consistent loops, but they raise eerie questions. If information or objects can exist without origin, does that mean some parts of history are predetermined? Could the universe be filled with artifacts that have no true creator? These paradoxes aren't just brain teasers, they're clues. They hint that time might be more resilient than we think, bending but never breaking under the weight of our meddling. Some theories, like the Novikov self-consistency principle, argue that any attempt to change the past would fizzle out, with the universe correcting itself to avoid contradictions. Others suggest branching timelines where every choice spawns a new reality, leaving the original history untouched. But one thing's clear: if time travel is possible, it likely comes with rules that keep the fabric of existence from unraveling at the seams. And that's the real puzzle. Time travel isn't just about bending physics, it's about whether reality itself can handle the chaos of a paradox. Maybe the universe has built-in fail-safes, or maybe we're just not asking the right questions yet. Either way, these mind-bending contradictions prove one thing: time isn't just a river we can paddle upstream, it's a labyrinth, and every turn comes with its own surprises. Quantum mechanics doesn't just challenge our understanding of particles, it shatters our perception of time itself. At the subatomic level, particles behave in ways that seem to defy logic, existing in multiple states at once or influencing each other instantaneously across vast distances. These bizarre phenomena, like superposition and quantum entanglement, hint that time might not flow the same way for tiny particles as it does for us. Imagine tossing a coin before it lands. It's neither fully heads nor tails, but a blur of both possibilities. That's superposition in action. Now, stretch that idea to time itself. Could a particle exist in multiple moments simultaneously, as if the past, present, and future are all overlapping? The delayed choice quantum eraser experiment takes this strangeness to another level. In this setup, particles like photons are sent through a maze of detectors, but here's the twist. Decisions made after the particle's journey seem to retroactively determine its path. It's as if the particle knows what choice the experimenter will make in the future, adjusting its behavior in the past accordingly. This isn't just a parlor trick. It suggests that at the quantum level, cause and effect might not be as rigid as we thought. Time could be more like a tangled web, where events aren't strictly linear but interconnected in ways that defy our everyday intuition. Then there's entanglement, the eerie phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, their properties sync up instantly, no matter how far apart they are. Change one, and the other responds immediately, faster than light, as if space and time don't apply to them. Some physicists speculate that entangled particles might be tapping into a deeper layer of reality where time isn't a straight line but a fluid, malleable dimension. If that's true, could we one day harness this connection to send information, or even ourselves across time? Of course, scaling these quantum quirks up to human-scale time travel is a monumental leap. We're still grappling with how to reconcile the fuzzy, probabilistic world of quantum mechanics with the smooth, predictable universe we experience. But the very fact that particles seem to dance outside the bounds of time raises a tantalizing question. What if time as we know it is just an illusion, a side effect of our macroscopic perspective? Maybe the universe's true clock ticks in ways we're only beginning to glimpse. And if that's the case, the future of time travel might not lie in massive wormholes or black holes, but in the strange, shimmering realm of the quantum. Closed time-like curves sound like something ripped straight from a time traveler's wildest dreams, paths through spacetime that loop back on themselves like a cosmic Möbius strip. These bizarre structures, often abbreviated as CTCs, emerge straight from Einstein's equations of general relativity, revealing that under specific conditions, time might not just flow forward, it could twist into a circle, allowing you to return to your own past. Picture walking down a path that somehow brings you back to the exact moment you started, with no breaks or paradoxes, just a seamless loop where cause and effect dance in perfect, mind-bending harmony. The idea gained serious traction when physicist Kip Thorne and his colleagues explored whether these curves could exist without breaking the universe's rules. Their thought experiment was as daring as it was simple. Could a sufficiently advanced civilization, armed with exotic matter and godlike engineering, construct a stable CTC? Thorne's calculations suggested something startling. Yes, in theory, it's possible, but there's a catch. These loops require conditions so extreme they border on fantasy. You'd need matter with negative energy density, a substance that defies gravity by repelling rather than attracting. While tiny amounts of negative energy might exist in quantum fluctuations, scaling it up to warp spacetime into a closed loop is like trying to build a bridge out of soap bubbles. Even wilder is the fact that closed time-like curves don't just permit time travel, they demand it. If you entered one, you wouldn't have a choice. Your future would become your past, forcing you to relive events in an endless cycle. And here's where things get trippy. Unlike the paradoxes that plague other time travel theories, CTCs might enforce a strange kind of cosmic consistency. The universe could edit your actions on the fly to ensure they fit seamlessly into the loop. Want to go back and stop your younger self from stepping into the curve? Too bad the equations suggest you'd fail, or your interference would somehow already be part of history. It's as if spacetime has a built-in undo button, but only for edits that keep the timeline intact. So why hasn't a time traveler from the future shown up to settle the debate? Maybe because closed time-like curves are less like highways and more like tightropes. Any slight disturbance, any stray atom out of place, and the loop snaps. Or perhaps they're hidden in places we can't reach, like the hearts of rotating black holes or the scrambled remnants of the Big Bang. Whatever the case, their mere existence in the math hints at a universe far more flexible and mysterious than we ever imagined. They remind us that time, for all its apparent rigidity, might just be waiting for us to learn its secret rhythms. Imagine a cylinder so massive and spinning so fast that it literally drags space-time along with it, twisting the fabric of reality into a loop where past and future collide. This isn't the plot of a sci-fi novel, it's the essence of Tipler's cylinder, a mind-bending concept dreamed up by physicist Frank Tipler in the 1970s. At its core, the idea is astonishingly simple. Take an infinitely long cylinder made of ultra-dense material, set it rotating near the speed of light, and watch as space-time itself warps around it. The sheer momentum of this spinning behemoth would create a whirlpool in time, bending it into a closed curve where you could, in theory, travel back to an earlier moment simply by circling the cylinder like a cosmic maypole. But here's the catch: building one would demand energy and materials far beyond anything humanity can muster. The cylinder would need to be impossibly dense, packing the mass of several suns into a structure just a few kilometers wide. To spin it fast enough to twist space-time, you'd need forces strong enough to shred ordinary matter into subatomic confetti. Even if you could somehow gather enough material, say, by dismantling entire stars, keeping the cylinder from collapsing under its own gravity would require a substance with tensile strength beyond anything known to physics. And that's not even the wildest part. Tipler's calculations showed that the cylinder couldn't just be long, it would have to stretch on forever, an infinite backbone threading through the universe. No finite version, no matter how massive, would do the trick. For a species confined to a finite planet in a finite solar system, that's an insurmountable hurdle. But let's say you somehow overcame it. Now you're left with navigation challenges straight out of a nightmare. Approach the cylinder at the wrong angle, and its gravitational tides would stretch you into spaghetti. Time loops might exist, but surviving the trip is another story entirely. Yet for all its impracticalities, Tipler's cylinder isn't just a fanciful thought experiment. It's a stark reminder of how deeply time and space are intertwined, how mere motion, amplified to cosmic extremes, can warp the very flow of causality. The universe seems to whisper that time travel might be possible, but it taunts us with conditions so extreme they feel like nature's way of saying, not yet. Or maybe not like this. One thing's certain: if we ever crack the code, it won't be with a cylinder, but the fact that the math allows such a possibility at all. That's enough to keep the dream alive. Cosmic strings are among the most peculiar relics the universe might have left behind, threads of pure energy thinner than an atom but stretching across unimaginable distances, remnants of the violent symmetry breaking moments just after the Big Bang. Picture them as cosmic fault lines, scars from when the newborn universe cooled and settled into its current state. These strings aren't just theoretical oddities. Their gravitational pull could warp space-time so drastically that if two of them were to slide past each other at near light speeds, they might twist the fabric of reality into a closed timelike curve, a loop where time folds back on itself, creating a shortcut to the past. The math behind this is as elegant as it is mind-bending. In the 1980s, physicist J. Richard Gott showed that two infinitely long cosmic strings moving in opposite directions could create a space-time geometry allowing for time travel. The strings' immense gravitational fields would act like cosmic spinning rods, dragging space-time along with them. If you were to circle around the strings in just the right way, you'd find yourself returning to the same point in space but also the same moment in time. It's like drawing a circle on a piece of paper, then twisting the paper so the ends meet not just in space but in time. But don't start plotting your historical sightseeing tour just yet. Cosmic strings, if they exist at all, are elusive. Unlike black holes or neutron stars, they don't emit light or cast shadows. The only way to detect them would be through their gravitational fingerprints, tiny distortions in the light of distant galaxies or ripples in the cosmic microwave background. Even if we found one, the energy required to manipulate strings into a time loop would dwarf anything humanity could muster. We're talking about moving objects with the mass of entire galaxies at speeds approaching light. Then there's the question of stability. A time loop created by cosmic strings would be like walking a tightrope over a chasm. One slight miscalculation and the loop collapses. Quantum effects, random particles, even the act of observing the strings could disrupt the delicate balance needed to sustain the curve. And if you did succeed, the universe might still enforce its own rules. Just like with wormholes or closed timelike curves, any attempt to alter the past could be neutralized by self-correcting mechanisms, paradoxes snapping shut before they unravel causality. Yet the mere possibility of cosmic strings hints at something profound. The early universe was a place of unimaginable energy, where the laws of physics as we know them were still taking shape. In that chaos, fragments of space-time itself might have been stretched, knotted, or twisted into configurations we're only beginning to imagine. Whether these strings are out there, silent, invisible, and weaving time into loops remains one of cosmology's great unanswered questions. But the fact that the math allows it at all is a reminder. The universe is far stranger and far more generous with its mysteries than we could ever dream. Tachyons, the universe's ultimate rule breakers, are particles that don't just flirt with the speed of light, they leave it in the dust. According to theory, these elusive specks of matter are born moving faster than light, and they can never slow down to sublight speeds. Unlike everything else in the known universe, which obeys Einstein's cosmic speed limit, tachyons would treat light like a starting line, not a finish. But here's where it gets even stranger. If they exist, their relationship with time would be flipped. While we experience time moving forward, tachyons might perceive it in reverse, as if their existence was a film playing backward frame by frame. The idea emerged in the 1960s when physicists tinkering with Einstein's equations noticed something peculiar. The math allowed for particles with imaginary mass, a bizarre concept where mass isn't a fixed number but something rooted in the square root of -1. These particles wouldn't just defy gravity, they'd accelerate as they lost energy, shooting toward infinite speed as their energy dropped to zero. Picture a car that goes faster the less gas you give it. An absolute nightmare for traffic laws, but a tantalizing possibility for time travel. If you could harness tachyons, you might be able to send messages or even yourself backward through time. So why haven't we found them? For starters, faster-than-light particles would be achingly difficult to detect. Normal matter interacts with light, allowing us to see, measure, and study it. But tachyons, by their very nature, would move too quickly to leave a conventional trace. Any signal they emitted would arrive before the event that created it, scrambling causality like a radio broadcast playing the news before it happens. Even if they zipped right through our detectors, we might not recognize the data as anything but noise. Then there's the energy problem. As tachyons lose energy, they gain speed, which means the most detectable ones, the slower, higher energy ones, might be vanishingly rare. The majority would be hurtling through the cosmos at speeds so extreme they'd barely interact with anything at all. Some theories even suggest that tachyons could be entirely sterile, not interacting with normal matter in any way except gravity. If that's true, they'd be cosmic ghosts, invisible and intangible, their presence only hinted at by missing energy or unexplained gravitational ripples. But the most damning argument against tachyons isn't technical, it's philosophical. Their existence would wreak havoc on causality, the foundation of reality as we know it. If a tachyon signal could reach you before it was sent, you could theoretically respond to it before the original message even left. This isn't just a paradox, it's a universe where effect precedes cause, where the future reaches backward to alter the past. Physics tends to reject such scenarios not because they're impossible, but because they're too messy. The laws of the cosmos seem to favor order, even if the math occasionally whispers about chaos. Yet the fact that tachyons remain mathematically possible keeps the door cracked open. Maybe they're hiding in the quantum foam, flickering in and out of existence too quickly to catch. Or perhaps they're locked away in some higher dimension beyond our current tools to detect. Until we know for sure, they stand as a reminder. The universe's rulebook might still have pages we haven't turned. And if tachyons are real, those pages could rewrite time itself. Time crystals sound like something from a wizard's lab, structures that pulse and oscillate endlessly without any energy input, defying one of the most fundamental laws of physics. Unlike ordinary crystals, which are defined by their repeating patterns in space, time crystals repeat in time, flipping between states like a clock ticking forever without winding. The concept was first proposed in 2012 by Nobel laureate Frank Wilczek, who wondered, could there be a form of matter that breaks time symmetry, not just space symmetry? The idea was initially met with skepticism. After all, perpetual motion machines are impossible, right? But here's the twist: time crystals don't actually violate thermodynamics. They don't create energy, they just dance in a never-ending loop, locked in a quantum rhythm that the universe itself seems to conduct. Imagine a snowflake that doesn't just sit frozen on a window pane but melts and reforms in perfect sync with some hidden cosmic metronome. That's the essence of a time crystal. In lab experiments, scientists have created them using chains of ions or atoms chilled to near absolute zero and then nudged with precise laser pulses. Instead of settling into equilibrium like normal matter, the atoms keep flipping between configurations, echoing the laser's rhythm but at a slower, more deliberate pace, like a pendulum swinging long after the hand that pushed it has let go. This isn't magic, it's a delicate quantum ballet where entanglement and many body interactions lock the particles into a pattern that time itself can't erase. Now here's where it gets wild. Time crystals might hold the key to understanding time's arrow, why we remember the past but not the future. Normally, the second law of thermodynamics dictates that disorder increases over time, giving us a clear direction from past to future. But time crystals exist outside this flow. Their oscillations are stable, immune to entropy's usual decay. Some physicists speculate that if we could scale them up, way up, they might serve as frameworks for quantum memory or even as probes to study the fabric of time itself. Picture a network of time crystals acting like gears in a cosmic clock, each tick encoding information about how time bends or twists under extreme conditions. But the real kicker, time crystals might already exist in nature. Certain exotic materials, like the bizarre quantum spin liquids, could harbor hidden time crystalline phases. Even black holes, those infamous time warps, might exhibit similar behavior at their event horizons, where gravity and quantum mechanics collide. If we could tap into these natural time crystals, we might uncover clues about how time operates at the universe's most fundamental level, or whether it's even as linear as we think. Of course, we're still a long way from using time crystals to build time machines. Their oscillations are fragile, confined to the quantum realm for now. Yet their very existence challenges our understanding of what matter can do. They hint at a deeper layer of reality where time isn't just a backdrop but an active participant, where the universe's rules might be more flexible and far stranger than we ever imagined. And that's the beauty of it. Time crystals don't just tick, they whisper secrets about the nature of time itself, if only we're patient enough to listen. From Marty McFly's guitar riff in Back to the Future to the TARDIS materializing in a London alley, pop culture has turned time travel into a playground of imagination, one where the rules bend to serve the story. And while Hollywood's take on hopping through epochs is undeniably thrilling, it often plays fast and loose with real physics. Take the iconic DeLorean, for example. The idea that hitting 88 miles per hour could trigger a temporal leap makes for a great movie moment, but speed alone doesn't warp time. Gravity and relativity do. Real-time dilation happens when you're moving close to light speed or orbiting a black hole, not cruising down a suburban street. Still, films like these embed a kernel of truth. Energy is the currency of the cosmos. The flux capacitor might be fiction, but the notion that time travel demands colossal energy, that's straight from Einstein's playbook. Then there's Doctor Who. where time isn't just a highway but a living, breathing entity, a timey-wimey ball of wibbly-wobbly stuff, as the Doctor famously quips. The show's portrayal of time as fluid and mutable isn't entirely off base. Quantum mechanics suggests that at the smallest scales, cause and effect can blur, and some interpretations of relativity allow for closed timelike curves. But the series glosses over the brutal paradoxes that would arise from rewriting history on a whim. Rose saving her father in Father's Day should have unraveled her own existence, yet the TARDIS crew treats time like a sandbox with occasional resets. Compare that to, say, Primer, a film so obsessed with causal consistency that its time loops require spreadsheets to untangle. One prioritizes drama, the other physics. Books often dive deeper into the philosophical weeds. H.G. Wells' The Time Machine introduced the idea of time as a fourth dimension, a radical notion in 1895 that foreshadowed relativity. But Wells' time traveler hops centuries without aging, ignoring the inevitability of time dilation. Meanwhile, modern novels like The Forever War weaponize relativity, portraying soldiers who age months while decades pass on Earth. It's a hauntingly accurate depiction of warped time, one that films rarely attempt. And then there are the tropes. The butterfly effect has become shorthand for chaos theory, but it's often oversimplified. In A Sound of Thunder, stepping on a prehistoric butterfly alters an election. In reality, quantum fluctuations average out over macro scales. Parallel timelines offer an easy escape from paradoxes. Thanks, Avengers. In-game, yet the many worlds interpretation they borrow from is far weirder, suggesting every quantum decision spawns a new universe. Pop culture cherry picks the cool bits, leaving the nuances behind. What's fascinating is how these stories mirror our own grappling with time's mysteries. They get the feeling right, the awe, the terror, the longing to rewrite regrets even when the science is scrambled, and sometimes fiction nudges reality forward. The term wormhole was coined in a 1937 sci-fi story before Einstein and Rosen gave it equations. Maybe one day, Hollywood's wildest visions will seem as prescient as Wells' machine. Until then, they're a reminder: time travel captivates because it's not just about physics, it's about us, our dreams, our fears, and the timeless question, what if? History has a funny way of folding in on itself, leaving behind strange wrinkles that look an awful lot like time slips. Take that now infamous flicker of footage from Charlie Chaplin's 1928 film The Circus. In the crowd, just for a split second, a woman walks by holding what appears to be a cell phone, or at least something pressed to her ear. The grainy black and white clip went viral years later, sparking wild theories. Was she a time traveler, casually scrolling through text decades before the first mobile call? Skeptics pounced, pointing out it was likely just a portable hearing aid or a rolled-up program. But the image lingers, feeding that itch to believe the impossible. After all, why couldn't some future cinephile have popped back to see the tramp in person? Then there's the Moberly Jourdain incident, a Victorian-era ghost story with a time travel twist. In 1901, two English academics, Charlotte Moberly and Elena Jourdain, claimed they'd wandered into the gardens of Versailles and stumbled straight into the 18th century. They described seeing Marie Antoinette lounging under a tree, courtiers in powdered wigs, even the Petit Trianon itself frozen in its pre-revolution glory. Later, they swore the landscape had shifted around them, paths vanished, buildings morphed. Psychologists chalked it up to shared hallucination or heat stroke, but the women insisted they'd brushed against a rift in time. Their detailed accounts, published under pseudonyms, remain a rabbit hole for paranormal enthusiasts. These stories share a delicious pattern, they're almost plausible. The Chaplin time traveler could be a trick of the light. Moberly and Jourdain might have been primed by romantic histories of Versailles. But what makes them irresistible is how they tap into a deeper question. If time travel were real, wouldn't the past be littered with these glitches? Imagine some future tourist snapping selfies at the signing of the Declaration of Independence, only to be immortalized as a smudge in a painting, or a medieval monk's manuscript describing a sky chariot that sounds suspiciously like a helicopter. The internet loves these anomalies because they flirt with the idea that history isn't as fixed as we think, that somewhere, somehow, the timeline's already been tampered with. Of course, science demands more than grainy footage or feverish diaries. Real evidence would need to be irrefutable, an object with impossible isotopes, a language from the future, or better yet, a time traveler who doesn't vanish when the cameras roll. Until then, these historical hiccups are like cosmic winks, reminders that the past might be messier and far more mysterious than our textbooks let on. And who knows, maybe one day we'll find the proof we've been chasing, or maybe it's already here, hiding in plain sight, waiting for us to recognize it. The Philadelphia experiment sounds like something straight out of a sci-fi thriller, a secret World War II mission where the U.S. Navy allegedly teleported a warship across space and time, vanishing it from Philadelphia's docks only to reappear seconds later in Norfolk, Virginia. According to the legend, sailors were fused into bulkheads, driven insane, or even phased out of existence entirely. The story exploded in the 1950s, fueled by a mix of urban myths, dubious eyewitness accounts, and a notorious letter from a man claiming to be a former crew member who said the ship had been rendered invisible using powerful electromagnetic fields. But how much of this is fact, and how much is wild speculation spun from misunderstood science? Digging into declassified records, we find a kernel of truth, just not the kind conspiracy theorists want to hear. The Navy was researching degaussing techniques during the war, a process that made ships less detectable to magnetic mines. Some experiments involved wrapping vessels in coils to manipulate their magnetic signatures, which could theoretically distort light under extreme conditions. But the leap from invisible to mines to vanishing into another dimension is pure fantasy. Even Einstein's unified field theory, often cited as the project's secret backbone, was still in its infancy at the time, far from the practical weaponization the myth suggests. The Navy has repeatedly denied the claims, and most historians dismiss the story as a hoax. Yet it persists, a testament to how easily scientific curiosity can morph into cosmic legend when shrouded in secrecy. Then there's the Montauk Project, an even wilder offshoot of the Philadelphia lore. This tale, popularized in the 1980s, alleges that the government continued its time travel experiments at a shadowy facility on Long Island. Whistleblowers described sessions where subjects psychically linked to ancient civilizations, interfaced with alien technology, or even opened portals to alternate timelines. The stories are a chaotic blend of Cold War paranoia, occultism, and recycled sci-fi tropes with zero verifiable evidence. But what's fascinating is how these myths borrow just enough real science to feel plausible. The Montauk tales often reference Nikola Tesla's work on resonance and energy transmission, concepts that were groundbreaking even if they were never used to bend spacetime. The real irony, while these government projects are fiction, actual research into manipulating spacetime is anything but. DARPA and other agencies have funded studies on quantum entanglement, warp drive physics, and even cloaking technologies, just not the way pop culture imagines. The line between conspiracy and cutting-edge science isn't always clear, especially when experiments are classified. Maybe that's why these stories endure. They tap into a deeper unease. If governments could control time, would they ever tell us? Or would those experiments vanish into the shadows, leaving behind only rumors and the occasional sailor stuck in a bulkhead? Time isn't just a ticking clock. It's a slippery, subjective experience, something scientists have proven in bizarre and fascinating experiments. Take the infamous 1962 French cave study, where geologist Mitchell Siffer volunteered to live alone in a pitch-black underground cavern for 2 months. With no sunlight, no clocks, and no way to track the passage of days, his body's natural rhythms took over. At first, he tried to maintain a routine, sleeping and waking based on his best guess. But without external cues, something extraordinary happened. His sense of time began to warp. What felt like a 24-hour cycle to him was actually closer to 48 hours in the real world. His sleep patterns stretched, his meals became erratic, and by the end, he'd lost all connection to the calendar. When researchers finally retrieved him, he was convinced he'd been underground for weeks less than he actually had. This wasn't just a fluke. Similar experiments like NASA studies in the 1990s found that isolation drastically alters our perception of time. Volunteers living in closed habitats for months reported moments where hours felt like minutes or vice versa. Without the usual anchors, sunrise, sunset, schedules, the brain struggles to maintain a linear framework. It's as if time isn't an external force but a story our minds construct, one that can fray at the edges when stripped of familiar cues. And then there are the more extreme cases, like the Russian sleep deprivation experiments of the 1940s, where subjects were kept awake for days on end. As fatigue set in, their grasp on time dissolved entirely. One participant reportedly experienced entire days in what felt like seconds, while another lived through nightmares where past and future collided. These studies reveal an unsettling truth. Time, as we experience it, is fragile. It's not just about clocks and calendars, it's a delicate dance between our biology and the world around us. So what does this mean for time travel? If our own perception of time can bend so easily under isolation or stress, could extreme conditions like the gravitational pull of a black hole or the speed of light twist it even further? Maybe the first step to traveling through time isn't building a machine, but understanding the mind's role in shaping the very fabric of our reality. After all, if time can stretch and compress inside our heads, who's to say it can't do the same out there in the cosmos? What if the universe itself acts as the ultimate editor, ensuring that any attempt to meddle with time only reinforces history instead of rewriting it? That's the core idea behind the Novikov self-consistency principle, a mind-bending theory proposed by Russian physicist Igor Novikov in the 1980s. Imagine time as a pre-written novel where every chapter must logically flow into the next, no contradictions, no plot holes. According to Novikov, any actions taken by a time traveler would inherently align with events that already happened, seamlessly weaving their interference into the existing timeline. It's not that paradoxes can't occur, it's that the laws of physics simply won't allow them to. Picture this: you travel back to prevent a historic disaster, only to realize your efforts inadvertently set the very events in motion you hope to stop. Your presence, your actions, they were always part of the story. This isn't just speculation, it's a direct response to the infamous grandfather paradox. Under Novikov's framework, the universe would conspire to make sure your grandfather survives, whether through a misfired gun or a sudden change of heart. The math suggests that probability itself might bend to preserve consistency, like a cosmic safety net preventing reality from unraveling. The implications are both comforting and eerie. On one hand, it removes the existential dread of accidentally erasing yourself from history. On the other, it implies a kind of predestination, a universe where free will might be an illusion and every choice you make was already accounted for. Some physicists argue this principle resolves the chaos of time travel by making it paradox-proof, while others see it as a philosophical straitjacket, stripping away the unpredictability that makes time travel so thrilling in fiction. But how would this play out in reality? Take a classic scenario. A time traveler gives Shakespeare a copy of his own plays. Under Novikov's rules, the plays Shakespeare writes would have to match the ones the traveler brought, word for word. Any attempt to alter them would fail. Maybe the ink smudges or the bard mishears a line. The outcome is fixed and the universe ensures it stays that way. It's as if time has a self-correcting algorithm, tweaking probabilities in the background to keep the timeline intact. Critics of the principle raise valid concerns. If the universe is so adept at enforcing consistency, why haven't we encountered evidence of time travelers already woven into history? And how does quantum mechanics, with its inherent randomness, fit into a seemingly deterministic model? Novikov's idea doesn't answer everything, but it offers a compelling middle ground between the chaos of paradoxes and the rigidity of a single, unchangeable timeline. Perhaps the most fascinating aspect is how this principle mirrors our own experiences. Ever had a moment where a seemingly random decision later felt inevitable? Novikov's universe might operate the same way, where every twist and turn, even those introduced by time travelers, was always meant to happen. It's a humbling thought that the past, present, and future could be far more intertwined than we ever realized, bound together by laws we're only beginning to glimpse. What if every choice you've ever made, every path taken or abandoned, spawned an entirely new universe? This isn't just a sci-fi trope. It's the heart of the many worlds interpretation, a radical theory in quantum physics that suggests reality constantly splits into infinite parallel timelines. And when it comes to time travel, this idea flips everything on its head. Suddenly, the grandfather paradox isn't a universe-breaking glitch, it's just another branch in an ever-growing cosmic tree. Try to go back and prevent your own birth, and you'd simply split off into a new timeline where that version of you never existed, while the original universe carries on unchanged. The past isn't a fragile artifact, it's an unshakable foundation, with every possible alteration spawning a new reality instead of rewriting history. Consider Schrödinger's famous cat, both alive and dead in its box until observed. The many worlds interpretation takes this further. The cat doesn't collapse into one state, it splits the universe. One world has a purring feline, the other a tragic expiration. Now apply that to time travel. Every decision a traveler makes, whether stepping on a butterfly or saving a life, wouldn't alter their original timeline. Instead, it'd create a new, self-contained reality where those changes play out. Want to stop World War II? You might succeed, but only in a fresh universe where Hitler's rise was thwarted, while the original timeline rolls forward with its history intact. Paradoxes dissolve because every possible outcome gets its own world. But here's the catch: if the multiverse is real, true time travel, as we imagine it, returning to your past to reshape your future might be impossible. You're not rewriting history, you're just hopping lanes on an infinite highway. The you who left never gets to see the changes because they're always happening elsewhere. This could explain why we've never met a time traveler from the future. They might be out there, but they're not in our timeline. Their meddling spawns new branches we'll never witness, leaving our version of events untouched. Critics argue this interpretation feels like a cop-out, a way to dodge the messy consequences of causality. After all, if every action spawns a new universe, where's the stakes? But proponents counter that it's the only model that preserves free will without breaking physics. You can change the past, just not your own. And in a cosmos teeming with infinite versions of reality, maybe that's enough. The multiverse doesn't close the door on time travel. It just reveals a labyrinth behind it, one where every twist and turn leads somewhere new. Have you ever woken from a dream convinced you've lived those exact moments before? The same faces, the same room, even the same whispered words. That eerie sensation, déjà vu, feels like a glitch in the matrix, a fleeting glimpse of time folding back on itself. But what if these experiences aren't echoes of alternate timelines or repressed memories? Neuroscience suggests they might be something far stranger, your brain's own internal time machine misfiring. When a new scene feels oddly familiar, it's often because a part of your brain called the hippocampus, which sorts memories, briefly malfunctions. Instead of filing the moment as fresh input, it misfires and labels it as something you've already experienced. The result, a visceral, unsettling sense that you've stepped into your own past. Then there's lucid dreaming, where the boundaries of time seem to dissolve entirely. In these rare, vivid dreams, you become aware you're asleep, and with practice, you can even steer the narrative. Suddenly, you're not just observing a dream, you're rewriting it in real time, looping back to change outcomes or fast-forwarding to skip ahead. Some lucid dreamers describe weaving intricate, multi-layered dreams where hours pass in what turns out to be minutes of real-world sleep. The brain's perception of time stretches like taffy, untethered from the clock on your bedside table. Neuroscientists believe this happens because the prefrontal cortex, the region responsible for logic and self-awareness, stays partially active during REM sleep, creating a surreal hybrid state where time becomes fluid. But why does the brain bend time this way? Evolution might hold a clue. Some researchers argue that déjà vu acts as a kind of reality check, a way for the brain to cross-reference new experiences against stored memories, ensuring we don't mistake imagination for fact. Lucid dreaming, on the other hand, could be a byproduct of our brains rehearsing survival scenarios, running simulations where time is just another variable to manipulate. Think of it as your mind's stress testing lab, where the rules of cause and effect are optional. Of course, this doesn't stop dreamers from wondering, if our brains can warp time so effortlessly in sleep, could we harness that ability while awake? Ancient cultures certainly thought so. Tibetan Buddhists practiced dream yoga, a form of meditation aimed at controlling dreams to achieve spiritual time travel. Modern scientists are more skeptical, but studies show that skilled lucid dreamers can train themselves to revisit specific memories or even pre-live future events in their sleep. The catch, these aren't real leaps through time, just incredibly vivid rehearsals. Yet the fact that our brains can simulate the sensation so convincingly hints at something profound. Time as we perceive it might be less a fixed river and more a hall of mirrors, reflecting our expectations, fears, and even the quirks of our biology. So the next time you snap awake with the uncanny feeling you've been here before, remember, you haven't slipped through time. Your brilliant, baffling brain is just playing tricks on you, offering a tantalizing taste of what it might feel like if time travel were real. And who knows, maybe one day we'll decode these neural hijinks well enough to turn them into something more. Until then, our dreams remain the closest thing we have to a personal time machine. Building a time machine isn't just an engineering challenge, it's a battle against the universe's most unforgiving laws. Take wormholes, those cosmic shortcuts that could, in theory, connect distant moments in time. Keeping one stable long enough to step through would require something called negative energy, a hypothetical form of matter that repels gravity instead of attracting it. The problem, we've never observed negative energy in nature, and the tiny amounts theoretically possible in quantum experiments are trillions of times too weak to hold open a wormhole. To stabilize even a microscopic one, you'd need the energy equivalent of multiple suns compressed into a space smaller than an atom. It's like trying to prop open a black hole with a toothpick while standing in a hurricane. Then there's the issue of materials. Imagine constructing a structure strong enough to withstand the gravitational forces near a black hole or the tidal stresses inside a wormhole. Even our most advanced alloys would snap like dry spaghetti under those conditions. Carbon nanotubes and graphene come close in strength, but they're still light years away from what's needed. And let's not forget radiation. Any hypothetical time machine skirting a black hole's edge would be bombarded by high-energy particles moving at nearly the speed of light, frying electronics and passengers instantly. Shielding against that would require materials with properties we can't even synthesize yet, like perfect superconductors or metamaterials that bend spacetime itself. Energy is another deal-breaker. Say you wanted to accelerate a spacecraft to near light speed for relativistic time travel. even with futuristic propulsion like antimatter engines, you'd need more fuel than exists in the observable universe to reach those velocities. The numbers are staggering. Accelerating a single human to 99.9% of light speed would require energy equivalent to converting the mass of Jupiter into pure energy. And that's just for a one-way trip forward in time. Reversing the flow would demand even more absurd resources. But perhaps the biggest roadblock is causality itself. The universe seems hardwired to prevent paradoxes, and every theoretical workaround, wormholes, closed time-like curves, cosmic strings, comes with a catch that feels like physics slamming the door shut. Maybe that's nature's way of telling us some boundaries aren't meant to be crossed. Or maybe we're just waiting for the next Einstein to show us a loophole we haven't dreamed of yet. Until then, time travel remains locked behind a vault of energy, materials, and cosmic rules we can't yet crack. If time travel were possible tomorrow, who gets to decide its rules? The ethical dilemmas surrounding tampering with history are as vast as they are unsettling. Picture a world where governments could erase defeats, corporations could patent past discoveries, or extremists could rewrite entire cultures by eliminating pivotal figures. The power to manipulate time wouldn't just change history, it would concentrate unimaginable control in the hands of those with access to the technology. Philosophers have wrestled with this for decades, warning that causality isn't just a scientific principle, it's the backbone of moral responsibility. If you could undo a genocide or prevent an assassination, the ethical imperative seems clear. But what if saving one life inadvertently triggers a worse catastrophe? The ripple effects could unravel civilizations. Consider the darker possibilities. Time travel as the ultimate weapon. Imagine a nation retroactively sabotaging rivals' industrial revolutions or silencing revolutionary ideas before they spread. History isn't just a record, it's a battleground where small changes could skew power for millennia. Ethicists like Nick Bostrom argue that meddling with causality introduces existential risks, scenarios where even well-intentioned edits might collapse the foundations of society. A single alteration could erase the conditions that made democracy, science, or human rights possible. Would we trust any institution, no matter how benevolent, with that kind of power? Then there's the question of consent. If you travel to the past, every interaction becomes an uninvited intrusion. The people of that era didn't choose to be part of your experiment. Philosopher Judith Jarvis Thomson's famous trolley problem takes on new dimensions here. Is it ethical to sacrifice historical authenticity to save lives? And what about the cultural theft that could follow? Time tourists might plunder lost art, exploit ancestral knowledge, or turn sacred moments into theme park attractions. The past isn't a simulation, it was someone's present, with all the dignity and complexity that entails. Even if we navigated these pitfalls, the psychological toll could be crippling. Historian Yuval Noah Harari posits that shared narratives bind societies together. Tampering with collective memory, say, by proving a founding myth was fabricated, might shatter the trust holding communities intact. Would humanity survive knowing its identity was malleable, its heroes and villains interchangeable? The weight of such power might fracture our very sense of reality. Perhaps the most haunting question isn't whether we can control time, but whether we should. The universe's laws might allow loopholes, but ethics offers no easy exits. Until we can answer these dilemmas, time travel remains not just a scientific challenge, but a mirror reflecting our deepest fears about power, justice, and who gets to write the story of us all. Could we ever crack the code of time travel, or is it forever out of reach, locked behind mysteries we've barely begun to understand? The answer might lie in two of physics' greatest unsolved puzzles: dark energy and quantum gravity. Right now, dark energy is the universe's most enigmatic force, driving galaxies apart at an accelerating rate. If we could somehow tap into its power, or even understand how it works, we might uncover the energy source needed to warp spacetime on demand. Some theorists speculate that dark energy could hold the key to stabilizing wormholes or creating exotic matter with negative energy, the very ingredients our hypothetical time machines would need. But here's the catch: we don't even know what dark energy is, let alone how to harness it. Until we do, it's like trying to build an engine without knowing what fuel it runs on. Then there's quantum gravity, the holy grail of theoretical physics. Einstein's relativity explains the cosmos on a grand scale, while quantum mechanics rules the subatomic world. But the two theories clash violently when pushed to extremes, like the singularity inside a black hole. Bridging that gap could reveal new layers of spacetime structure, perhaps showing us loopholes in causality we've never imagined. Nobel laureate Roger Penrose has suggested that quantum gravity might allow for conformal cyclic cosmology, where the universe endlessly resets itself, a kind of natural time loop. Others, like physicist Lee Smolin, argue that time might emerge from quantum entanglement itself, a web of connections where past and future are more fluid than we think. So when, if ever, could these breakthroughs happen? Optimists like Michio Kaku suggest that with exponential advances in AI and quantum computing, we might uncover the math for time travel within this century. Skeptics counter that the energy requirements alone make it practically impossible, like trying to boil the ocean with a match. But history has a way of humbling predictions. 100 years ago, black holes were considered mathematical oddities. Today, we've photographed one. The leap from impossible to inevitable might just be one paradigm shift away. Perhaps the most tantalizing clue comes from the universe itself. If time travel is possible, even in theory, why haven't we met visitors from the future? Some say it's proof the laws of physics forbid it. Others wonder if we're simply not looking in the right places, or if future travelers are too careful to reveal themselves. Until we know for sure, the dream remains alive, suspended between the equations we've written and the ones we've yet to discover. Among the wilder corners of time travel lore, few stories capture the imagination like John Titor, the self-proclaimed time traveler from the year 2036. In the early 2000s, posts began appearing on internet forums under his name, detailing a world where civil war had fractured America, and a bizarre device known as a C-204 time displacement unit allowed jumps between timelines. Titor's predictions ranged from eerily specific, like a United Nations-led conflict in 2015, to the outright absurd, like a secret IBM project involving vintage 510 computers. What made his claims so magnetic wasn't just the dystopian future he painted, but the way he wove in just enough real physics to sound plausible, referencing Einstein's equations and the many worlds interpretation. Yet when his deadlines passed without event, no civil war, no time machines at IBM, the legend unraveled. Most now agree Titor was an elaborate hoax, a cautionary tale about how easily technical jargon and apocalyptic imagery can blur the line between fiction and fringe science. Then there's the even more outlandish theory that UFOs aren't extraterrestrial at all, but visitors from humanity's own distant future. Proponents point to the sheer familiarity of some reported encounters, humanoid figures piloting crafts, or even interacting with witnesses in modern languages. If aliens crossed light years to reach us, why would they look so much like us? The idea gained traction in the 1960s when French UFO researcher Jacques Vallée suggested that these phenomena might be interdimensional or temporal rather than interstellar. Fast forward to modern accounts, like the infamous 2004 Nimitz incident, where pilots described a tic-tac-shaped object displaying physics-defying maneuvers. Could those sudden accelerations and instantaneous disappearances be signs of technology manipulating spacetime itself? Skeptics dismiss the notion, arguing that leaping to time travelers as an explanation ignores simpler possibilities, misidentified military tech or atmospheric anomalies. But the most glaring hole in these theories is the lack of tangible evidence. If future humans had the means to visit us, why leave only blurry footage and cryptic stories? Why not share cures for diseases or warnings about impending disasters? The silence speaks volumes, yet the persistence of these ideas reveals something deeper, a longing to believe that time isn't just a one-way street and that somewhere, somehow, the future is already within reach. Whether through hoaxes, misidentifications, or genuine mysteries we can't yet explain, these fringe theories keep the dream alive, reminding us that the universe and time itself might still have surprises in store. The universe doesn't need a time machine to bend the rules, it's already doing it. Take gravitational lensing, one of nature's most elegant illusions. When light from a distant star passes near a massive object like a galaxy or black hole, space-time bends so dramatically that the light curves around it, like a marble rolling along a warped sheet. But here's the twist: that distortion doesn't just alter the light's path, it slows it down. To an observer, the star's light might appear delayed by years or even centuries, creating a cosmic echo where we're literally seeing the past. In extreme cases, like the galaxy cluster MAX J0717, astronomers have spotted multiple images of the same supernova, each showing the explosion at a different point in time, a natural time-lapse replay written into the fabric of spacetime itself. Black hole mergers take this time-warping spectacle to another level. When two black holes spiral toward collision, they churn spacetime into a whirlpool of gravitational waves, ripples that stretch and compress time as they travel. The energy released is so immense that it briefly distorts the flow of time across the entire universe. During the historic LIGO detection in 2015, scientists measured these waves and found something astonishing. The final milliseconds of the black hole's dance stretched time so drastically that a single second near the merger would feel like an eternity for a distant observer. It's as if the universe pressed pause, offering a fleeting glimpse of how gravity can manipulate time like clay. Even Earth isn't immune to these subtle time shifts. GPS satellites orbiting 12,000 miles above us have to account for relativity every single day. Because they're moving faster than objects on the ground and experiencing weaker gravity, their onboard clocks tick about 38 microseconds faster per day than those on Earth. Left uncorrected, this tiny discrepancy would throw off navigation by miles within hours. It's a daily reminder that time isn't absolute, it's fluid, shaped by speed and gravity in ways we've learned to harness but are only beginning to understand. Perhaps the most mind-bending natural time warp lies in the heart of pulsars. These rapidly spinning neutron stars beam out radiation like cosmic lighthouses with such precision that their pulses can serve as interstellar clocks. But when a pulsar orbits another massive object, like the famed binary system PSRB 1913+16, spacetime's curvature causes its signals to arrive slightly early or late, depending on its position in orbit. Tracking these delays over decades has given us some of the strongest evidence for gravitational waves and revealed how spacetime itself breathes and flexes around dense objects. These phenomena aren't just cosmic curiosities, they're blueprints. If we could replicate the conditions of a black hole merger or amplify the time-bending effects of gravitational lensing, might we engineer our own controlled time distortions? Nature's already written the playbook, we just need to learn how to read it. Every flickering quasar, every delayed GPS signal whispers the same truth: time travel isn't a violation of physics. It's happening all around us, woven into the universe's deepest rhythms, and that changes everything. So what would you do with a time machine? Would you step into the future to glimpse the fate of humanity, or wander the halls of ancient Alexandria before its great library burned? Maybe you'd rewrite a personal moment, or simply sit quietly in the Cretaceous period, watching dinosaurs roam under an alien sky. The possibilities are dizzying, but here's the fun part: you don't need a DeLorean to play this out. Drop your answer in the comments, tell us which era calls to you, or what twist of history you'd untangle if given the chance. And while you're at it, let's settle the ultimate debate. Would you actually hit the time travel button if it were real, knowing the risks? Vote in the poll below. Are you team rewrite history or team never mess with causality? Some of you might already have wild theories brewing. Maybe you're convinced time travelers are secretly among us, or that déjà vu is proof the timeline's been tampered with. Share those too. The best ideas often come from the cracks between science and imagination, and who knows, your off-the-wall thought might just spark someone else's breakthrough. After all, Einstein daydreamed about chasing light beams before relativity clicked into place. So don't hold back. Whether you're team wormhole or team cosmic strings, team it's all impossible, or team I've already time traveled from next Tuesday, this is your moment to weigh in. The comments are open, the poll is live, let's see where the collective imagination takes us. Time travel isn't just a fantasy, it's a frontier where science and imagination collide. We've seen how relativity warps time near black holes, how wormholes might stitch together distant moments, and how quantum mechanics blurs the line between past and future. The math says it's possible, but the universe throws up roadblocks at every turn. Paradoxes that snap causality like a twig, energy demands that dwarf stars, and materials that don't yet exist. Yet for all the obstacles, the fact that physics even allows these possibilities is staggering. It's as if the cosmos is teasing us, dangling the keys to time just out of reach. Think about how far we've come. A century ago, Einstein's ideas were met with disbelief. Now we've measured time dilation with atomic clocks on airplanes. Black holes were mathematical oddities. Today, we've captured their shadows. Every leap in understanding peels back another layer of spacetime's mysteries. Who's to say the next breakthrough won't reveal a hidden path through time? Maybe the answer lies in dark energy or quantum gravity or some phenomenon we haven't even named yet. The universe has a habit of outpacing our wildest theories after all. Entanglement and expanding galaxies once seemed impossible too. So where does that leave us? Hopeful. The same laws that seem to forbid time travel also hint at workarounds, whispering that the story isn't over. Whether it's a future civilization harnessing cosmic strings or a lab somewhere cracking the code of negative energy, the door isn't shut. It's just waiting for the right key, and until then, the pursuit alone is its own reward. Every paradox we untangle, every equation we refine, brings us closer to understanding time's true nature, not as a rigid line, but as a fluid, dynamic dimension ripe for exploration. So keep dreaming, keep questioning, because if history's taught us anything, it's that the universe is stranger than fiction. And who knows, the next chapter in our quest to conquer time might be just around the corner, or already written, waiting for us to catch up.